Entropy, everybody thinks about as this kind of thermal heat with no correlations and all of that. And it seems to be completely opposite to the concept of coherence, where things are organized over large scales, but the two go together and it makes quantum mechanics and quantum cosmology, which is what quantum mechanics is, because cosmology is everything. And so that's the title. But the point that was not in the abstract, that I want to emphasize here, is something that, well, I think it's true for everybody in every age in science, that cosmic science is done by cosmic friends, that it's people who are close friends with each other that collaborate together. And usually it's sort of your era of PhD, post-PhD. But if you're lucky, your great collaborations extend throughout your entire working life. So I'm going to inject you with a very personal view of my development, which starts from actually being an undergraduate in Toronto. And it's a very personal kind of history, but it's all about how entropy has been underlying this. And there are many fellow travelers on this journey with me at the many places I've been at, and these are some of the lists of those places. Caltech is where George and I first crossed paths. So the general picture is one of quantum cosmology, and this is kind of things that you all know, but we should celebrate anyway. Unveiling fundamental physics from complexity to simplicity to complexity to simplicity. Simplicity may or may not be the ultimate long-term future. Complexity is whatever things emerged from. Simplicity is how simple that 7-parameter description is that has been so hard won by cosmology in what we'd like to call the golden age. That got culminated by the various microwave background experiments plus all the large-scale structure experiments. My goal is to actually write a book or maybe pamphlets or something, a tome. But it is the issue is whether it'll be interesting enough for other people to hear about. But what we're going to see is a lot of relationship of quantum mechanics to the flow of the universe. And so this is the master equation, which you've probably never seen before, which is the wave function of the universe is the exponent of the minus of the yin-yang symbol. And so that mysterious thing I'm going to try and someone explain, but this, number one, it kind of looks like an S, but I'll explain that it's even more profound than that. But the wave function is e to the I action minus, it's actually half entropy because it's the square root of number when you do the derivative. And so the two ingredients, which are fundamental in the title, phase, which is what action is, and information or entropy, that those go together and they make quantum mechanics. And so after all of the efforts in my career that took me, that these two clearly go together, which was obvious, I guess, from the beginning, but it takes a while to actually see things. And then you say, yeah, but everybody knows that. And the worst thing that you can say, well, it's just quantum mechanics. But the universe is just quantum mechanics, so it's not a tiny thing. And, Feynman, I quoted von Neumann in his response to Shannon about his information quantity, we should call it entropy. Feynman famously said, nobody understands quantum mechanics. And then there was the other dictum, which is shut up and calculate, which means that you try not to go down the rabbit hole of metaphysics, of physics, although you'll see that I'm probably going down that rabbit hole. Our goal, actually, from the beginning, using the CMB large-scale structure with this fantastic convergence towards a standard model, has always been to find something that's beyond that standard model. And we're still in quest of that. And I can tell you, if we don't get it, our subject is going to become anemic. So we need to find things to look for that are beyond the standard model of cosmology. And tilde lambda CDM, while great, is not got the sense of newness that we would like to have. Okay, so I'm going to go back to cosmic information and some of the people whose pictures you will recognize if we go into it in detail, but I don't have time for that. I'm going to emphasize, though, Pythagoras, because we are all Pythagoreans. We ascribe to the fundamental view that you can describe the universe in terms of mathematics. He also introduced digital, that is to say, counting numbers, but also harmonics, you know, playing the string instrument. And so, you know, with the, and we'll see this later, 1, 2, 3 infinity ideas, he abstracted this to be a full description of the universe. And you say, well, oh yeah, but that's a long time ago. They didn't really know anything. And my contention is they actually knew a lot. It's just that they didn't know the microcosm and the macrocosm that we know now because we dug so deep, but the information is there at the meso level that we inhabit of, you know, what is fundamental in physics. The other person I'm highlighting here is somebody that if you read him, you say quite profound. Maybe it's just because he was Socrates' student, but he emphasized the concept of idea with a capital I from idea with a little I. And we just did a vlog with my good friend Brian here, and we got into this story that everything is information, and you're going to hear a little bit too much about that. Okay, so Plato, ideas, right? And that the asymptotic little ideas is capital idea, of which you probably never get to because it's too ideal. This is Fred Hoyle. This is Gamow. And I won't name the others, Lemaitre. So I'm not going to name all of these others. I'll name this character, Newton, just because you may have, I don't know if you have, you may have seen the movie, The Mask. You ever seen the movie, The Mask? My fellow Canadian starred in that movie. And so I was in Edinburgh behind curtain, as it were. And this is Newton's death mask. And so I was able to take Newton's death mask. And I did not get insight when I put it on my face and became the mask. But I find this a joyous picture, right? The connectivity that we all have to these characters, that's what we're trying to move forward. That's the goal of our existence. I could spend arbitrarily long time on everybody else here. Oh yeah, there's epsilon of t, which looms large. You all know about it. It's sometimes called the slow roll parameter. Complete misstatement of what it actually is. The parameter is the acceleration parameter of the universe. Epsilon approximately 0 is inflation. Epsilon equals 1 is end of inflation. Epsilon is 3/2 is ordinary cold matter. And epsilon of 2 is radiation. Epsilon of 3 is if it's completely kinetic and doesn't have the spatial Laplacians and gradients associated with that. Anyway, so epsilon extremely important for understanding evolution of the universe. Okay, so now I'm going to go back to how I learned about thermodynamics. And I'm going to emphasize some words here which you've heard, but I hope that they will really sink home. Gravity is not gravity. Thermodynamics is not thermodynamics. It's called gravothermal, and they're deeply connected to each other. And a long time ago in cosmology and the dynamics of galaxies, they understood that there was something they called the gravithermal catastrophe. And I'll get into this in more detail, but my view is that that's the fundamental thing that is defining how gravity is working and how the universe evolves. It is by a splitting of something that collapses into a core and something that has entropy radiated into it, which is effectively voids and things like that. So that's universal. We usually think about it in terms of the formation of red giant stars or in terms of very dense star clusters doing this gravithermal catastrophe, but in fact, it's very general. So these are some of the great champions. This was a textbook from me being an undergraduate of the thermodynamic history. This is Boltzmann. This is the great beginning of American physics, Gibbs. And you know all the names of all these characters. There's a name here which you know, but you probably don't know. This is Carnot's book, 1824. He was the one who introduced entropy, but he didn't call it entropy, somebody else did. So Carnot died extremely young, but made this profound thing by looking at heat and engines. And that's, of course, how you were taught thermodynamics back in the day. And one way of doing that, here we have what's called the ideal Carnot cycle for engines. And the ideal Carnot cycle has entropy in this direction, temperature in that direction, and it goes up and down, and it can go around and around and around. But in the real world, at the macroscopic level, there is always what is in effect, you might call it a hysteresis, in which the entropy is positive and increasing. And so that's sort of the thing that one learned about, but that wasn't the only thing that one learned about, because you're doing physics, you probably did chemistry. In chemistry, entropy plays an extremely important role, but that's not really the way one is wording it. It is the balance of chemical potentials which is occurring in reactions, where this is in ingredients, and this is the out ingredients for a reaction which is in thermal equilibrium. And so this is the sort of thing that I was steeped in my youth at the University of Toronto as an undergraduate, curiously enough. I passed much of my career at the same university I was an undergraduate in, which is a rare phenomenon. I don't know how many of you will have done something similar to that, probably not many. Some of the books that were on my shelf, not just this, which was the textbook of the time, is Fermi. Little book, really profound, but classical thermodynamics in the whole sense of the word and not into the statistical physics of the whole thing. And another book here. So I went from the University of Toronto to Caltech 50 years ago, 51 to be sure. And I was keen about seeing the universe as a coherent entity, all interacting together. And part of that was because as an undergraduate, among other things that I worked on superfluids. And so superfluids are supposed to be this collective quantum phenomenon that's effectively macroscopic, just like superconductors are. And so I was intrigued by that. And then with the neutrinos, the way I was envisioning it through my thesis and all of that, it was that the neutrino comes in, it tickles the medium, and the medium as a unit and a collective responds, which is what happens, and you can describe it in terms of current correlation functions, response functions. So I'm getting a little bit too technical here. But then, as you will see, what should have happened right at the beginning, because I was well steeped in it, but the entropic went closely connected to the coherent. But why we all became anthropologists will be revealed in the next slide. So then my whole career, out of all of the time from that period to now, with every problem that I've worked on, it is in order to go from the ultra early universe to the ultra late universe with these two concepts in mind to try and explain to myself, and hopefully to you, but to myself, how things are put together and how they work. So now I'm going to go back to the beta thing, which I was extremely pleased to join one George Fuller as a beta prize winner. But the reason for that is because beta did the most trivial thing imaginable. He took the entropy And he divided it by K Boltzmann and did it per baryon. And then said in a core collapse supernova, the entropy per baryon is about 1. And so you ask, well, what does that mean? I have this randomness, because you always thought about it as randomness back then. And then you have these baryons, and you have this amount of entropy that's, kind of associated with each baryon in the medium. And that's really quite remarkable because it's about 1. What does that mean? How much randomness does that mean? In the universe at large, as I think you all know, the entropy per baryon in the photons is about 10 to the 10th. And in neutrinos, it's about 10 to the 10th. So this is extremely small value relative to the universe at large. So I wasn't the only one that was struck by this. George got the lightning too, and he's followed his own entropic path. And then we are now colliding and working together. In fact, here is an example of a piece of work that took far too many years to complete, cosmic neutrino decoupling, and its observable insights from entropic dual transport, which I will try and explain to you as we go. But there's much to talk about in this picture. This is this thesis advisor of me and George, Willie Fowler. That's why he gets 3 rings. He's got thesis advisor and also did remarkable things. The remarkable thing in the blue is connecting him to Fred Hoyle and 2 of the stalwarts of UC San Diego, the 2 Burbages, who were working within the context. Here's another guy, Cameron, who also was heavily involved in this, understanding how all of the chemical elements were formed in stars. What an amazing thing to do. And something that, we still work on, but nonetheless, it was a tremendous breakthrough, a grand unification of its time. I gave this talk at this Peebles, who also worked on Big Bang nucleosynthesis, and there was also some work in Russia, but there was this huge effort by Bob Wagner, and I gave this talk last week in Stanford, and Bob was in the audience, a very good friend of mine. But Wagner, Fowler, and Hoyle was one of the key things. And the remarkable thing is that Wagner's code done in, I don't know, Fortran 60, if there is such a thing, ancient thing.
66.
But it got passed from generation to generation, and it's still even being used. It's remarkable. Anyway, that's another unbelievable story, the light element nucleosynthesis. But I will now turn, so this is all about the nuclear era, nuclear astrophysics, because particle astrophysics grew out of nuclear astrophysics. And neutrinos were the story of the day. But I'm now going to extol the virtues of this character, as we discussed with Brian today, George Gamow, who wrote a book that was incredibly influential, 1, 2, 3 Infinity, the most brilliant title imaginable for a book that's trying to describe how you would go from thinking as humans think into trying to understand the cosmos at large. He wrote the book, a popular book, too early. So the grand unification of ideas had some, false steps, but he was trying to go from the beginning through the formation of the Earth and formation of life. And he had the whole sweep in it, and it had a huge impact, not just on me. It was written around, late 40s, early 50s. So I was still a figment of people's imagination at that time. But he also put together, anyway, the book excited people like David Gross and other major figures in astronomy. So this was big impact, very smart guy. He had the wisdom to try and explain all of the light elements, which at that time they were trying to explain all of the elements. And he had the wisdom to join Alfred, his student, with him to get beta on it. So it become the alpha, beta, and gamma paper. And one of the things that came out of this, 5 degrees Kelvin, it wasn't out of that paper, it was a little bit later, but the recognition that there would be a relic radiation And it could have been found, it was actually found in cyanogen lines that was known, but nobody put it together until the Penzias and Wilson discovery. Anyway, that's too much on that topic. So nuclear astrophysics, transport, that's the issue. So this is me at the Cosmic Web conference in 2023. My good friend Brent Tully took a picture that happened to superimpose the S for entropy, or supergravity or whatever, showing that I am not just a minor anthropologist, but it is a complete passion. I'm going to go to this in a second, but well, this is what I'll go to now. So the yin yang aspect of this, what does that mean? Universe, whole thing, is signal plus noise, system plus reservoir, and if you think about it right, particles and holes, because particles and holes are not just fermionic, but they can actually be bosonic as well. And so it's a description, you can say, well, what kind of an equation is that? Because it's quite descriptive. But it's actually sort of got everything in it. And you can see that the S is at the top for either Superman or, in this case, supergravity or some such thing with this equation here. But so I was pushing this case, and then I ran across, we were doing a memorial for a very good friend of mine, Mick Kaiser, and I ran across that Bohr had made a coat of arms in 1947. And this is his coat of arms. And look what's in the center of the coat of arms. So his vision of complementarity and all of that in quantum mechanics all revolved around yin yang too. Now I could say it's exactly the same, but it probably isn't. But nonetheless, that was neat. Opposites are complementary and all of that. The opposites being this on that side, etc. And I completely ascribe to that, but ascribe to it in a slightly different way than they do. And I added to the coat of arms some other thing associated with my good friend Nick Kaiser. But let me just riff on this for a second. So the boundary between signal and noise, or system and reservoir, is kind of arbitrary. So system can be small number of variables, reservoir huge, the rest of the universe. And one of the terminologies that's appeared in quantum information is that you have, this would be called in that game a bipartite boundary. That is to say, it's a boundary of two. And what you think about is that there are fluctuations of all scales all along this boundary, and they're all talking to each other. And the system kind of responds with a question, and the universe acts back, is Mother Nature, with a response, system response, or reservoir. But what is system and what is reservoir? It could be reservoir and system, that is to say they're complementary in this sense. And this sounds a bit mysterious. It also sounds like I'm dangerously moving towards metaphysics, which I probably am, because I'm of an age. But I guess I wanted to say the following thing. In 1980, I gave a talk at the beginning of the Institute for Theoretical Physics, the very first program. And it was on supernova and core collapse, and Hans Bethe was holding court. And I came down from Berkeley at the time. I had been at Caltech and went up to Berkeley and gave a talk, Entropy, Neutrinos, and Supernova, which was trying to be a grand unification of ideas then. And there were even some ideas that the great Bethe hadn't thought about. That was 80. And then just to show that I have been dealing with the same ideas forever, I gave a talk at KITP. It was an inflation thing. It was entropy, phonons, and phase transition. Phonons being the quanta of energy. And that is, in fact, how the whole inflationary things work. You make energy phonons, which is what is is doing the formation of structure in the universe. Anyway, I could go on for all sorts of things about transport, but I wanted to mention this, and because I'm going to riff on this. Well, this is Bohr, who we talked about. This is Wheeler. I'm going to extol the virtues of Wheeler, and it isn't just that he was Feynman's thesis advisor. He was one of the great creative spirits in physics of all times. So they did fission together, and if you think about it, what is the universe doing? It's making fission fusions, fission fusions. That's essentially the yin-yang aspect of it. Coming together, going apart, coming together, going apart. You'll see this in more detail later as I get into the ultra universe. Wheeler said the 30s was his period of particles. That's when he was doing fission, nuclear physics, and all of that. And then he said the 50s was his period of doing fields, because he got into classical gravity at that time. Ultimately, that became the black hole paradigm. But there was this incredible grouping at Princeton at that time, not the least of which was Einstein, still there, but there was Dickey, who basically did the fundamental instrumental thing that made possible the discovery of the microwave background. The great Dickey, in the Browns-Dickey theory and all of that stuff, tremendous person. And then he was operating at the same institute. I don't know if they, according to Peebles, they didn't necessarily talk that much together, but he was doing, gravity and these incredible visions of geons, which would be these relativistic things that would be sort of torus. Anyway, I could wax eloquent on that, but he said the 70s, he got into quantum information and saw everything as quantum information, which is what I'm going to turn to now. A little bit more on the quantum information side. And I'm going to actually read this. So this is you probably recognize this person. That's Yukawa, and that's Wheeler. They're kind of strolling the grounds of the Institute for Advanced Study. But that means that this guy and this guy were at some level A, colleagues, and B, probably resonating. I don't know the level at which they were talking to each other. And there's Yukawa in Princeton chatting to them all. It was, this fantastic grouping. So this is what Wheeler wrote in the 70s. Now I am in the grip of a new vision, that everything is information. The more I have pondered the mystery of the quantum and our strange ability to comprehend this world in which we live, the more I see possible fundamental roles for logic and information as bedrock of physical theory. What I like best about this line is that it ends with, I continue to search, which allows we of an age to say, all pedal to the metal as we go forward. So I didn't actually come across this. I should have come across this a long time before, because so many people I knew very well were Wheeler students. And almost en masse, they moved into quantum information. And that actually kind of spearheaded much of the development of quantum information that very many people subsequently went into. Now it's one of the big subjects. Wheeler famously came up from it from bit, which is the it being the universe and the bit being its information, which is giving it. And I added my little riff to that, which is from bits in it, the bits being the information that flows to us within the universe itself. And that it's a symbiotic coupling of the information flows. Now, this will really tell the age. Who has ever heard of laughing? See, young people have not. It was like the precursor to Saturday Night Live, and it was in the 60s. And had famous people on it. Goldie Hawn was one of the stars. It was a comedy, or at least supposed to be a comedy. But they made a lot of fun of Marshall McLuhan, who was incredibly famous for, his cryptic comments. He was an English professor at the University of Toronto. And everything was all about media.
So TV was called cold media, movies hot media, and he was describing how all of this was taking over. It's completely taken over now, our reality. But I read this in a different way. The media is the message. The message is the physical underpinning of the universe. It's information. It is Wheeler, writ large. And that is, and essentially what is happening in this room is the condensation of information. Information flows, but information can also get into patterns that are essentially in equilibrium. Von Neumann's entropy quantum is trace rho log rho inverse. The reason for putting the inverse there is because it reminds you that entropy is really about phase space volume. And so the inverse of a density is a volume, and the density splits up into a density of reservoir given system and density of the system. That's the base theory. And so that's the basic split that we're talking about. But rho has within it two entities, and that is it's got differential phase, and it's also got probability, which is the counting. Therefore, it's fully describing all of quantum mechanics. It doesn't do it by wave function. So all of the quantum information is in density matrices. So then Shannon comes along and is thinking about communication channels, and which a lot of people were doing at the time. And so he came up with, you have a probability in the log of the probability final divided by the probability initial. That is an information content measure. And that this is related to that is something that I would say there was a lot of resistance to. And I didn't really realize this until much later in my entropic path, that it was all just the same thing. So now I want to go into another remarkable aspect of how entropy is entering into our existence. There was this famous little book, really little book, written in the 40s by Erwin Schrödinger when he was in Dublin, called What is Life? And it had this huge impact. And it was the main reason that a large number of physicists flowed into biology, including some of the greats at Caltech, but also including Crick and Watson. They got stimulated by this. Gamow, too, who was one of the champions of DNA in the 50s and organized a lot of people. But the essential idea is that life is a low entropy fluctuation that is fundamentally there. It's required in open systems. So humans are entropically cool and organized. What we do is we get radiated by high quality information, which is the radiation from the sun. I'm telling you things you already know, but maybe not, you haven't quite looked at it this way. So the waste heat that comes at us after we make use of it is it radiates out in the infrared. You know, there's albedo in the earth and all of that stuff. From humans, it radiates out in sweat, but photosynthesis and all of that is all about the use of high quality radiation. But before it's degraded into the waste heat transport. But it isn't just that. It isn't just that that's the Earth at large. It's also true that cosmic dust grains do exactly the same thing. A cosmic dust grain takes high quality information, mainly ultraviolet, but also optical information from stars, absorbs it, it rattles around in a dust grain, and it reaches an equilibrium thermal temperature, which is much, much lower than the quality of the radiations coming in. And so there's a tremendous entropy increase as a consequence of that. But along the way, there is the possibility of doing remarkable chemistry, just like there has been remarkable chemistry going on in the surface of the Earth. And, you know, one of the interesting issues is, do biological things form on dust grains? and maybe see the Earth. You know, this is a fun problem to think about. But at the very heart is the concept of a negative entropy fluctuation, which has the entropy radiating away, to be sure, but the key thing about life is that it's an entropy fluctuation downward. Then another topic, which is actually talked with Brian about today, is taking the ideas here and doing Everett and Wheeler. Everett was here in Princeton when he did the many worlds, right? That's what he did. And there was resistance to this, but now it's, I wouldn't say it's universally embraced, but many people embrace it as the basic idea. It's come under the label of multiverse. I don't like that label. It isn't, because there's only one universe. It's just that it's complicated. But anyway, I got into this in the 80s. Anyway, so that's enough of that. We'll see a little bit of that later if there's time, which there probably won't be. And these ideas of the interconnectivity of things, which we came to call the cosmic web, is now entered into descriptions of how you're supposed to understand English literature and other literatures. And so you're supposed to understand some of these great writers, D.H. Lawrence, Nabokov, Borges, Thomas Pynchon, by seeing how you translate the ideas, which I don't think this person understood that it was entropic in its origin, but that it's all interconnected. Of course, that's just kind of fantasy, maybe misuse, but it's not unlike what happened when relativity was discovered. Everything in the humanities got under the umbrella, philosophical umbrella, relativity in action. Okay, so around the time I transitioned to Berkeley, I did absolutely, you can call it really simple calculations, and they were, but you have to be careful. If you think about what is the entropy per baryon here in the air. And what you have to take into account is all of the degrees of freedom associated with molecules that are rotating, et cetera. It's surprising. In order to get the number, but that number is about 1. And so the ridiculous concept is that I can take some air, I can compress it adiabatically. I have to let a few leptons go away in order to make it more neutron rich. But essentially, I would then get a supernova core, which is kind of amusing. The entropy in the center of the sun is 19 per baryon. So you think, okay, well, that's more random stuff going on because it's really hot. I was asked by Lenny Susskind, yeah, but what is the photon entropy per baryon in the center of the sun? And I knew it was small, but I couldn't off the top of my head say what it was. It turns out to be about a 40th. What are the units of this? Entropy per baryon. Well, I came to learn that they are nats, called them natural units, but you can translate them into bits, which of course what people do all the time. And so you can translate everything into bits. In the center of clusters, the entropy per baryon is about 190. And the interesting concept that I would like to indicate to you is that there's actually an entropy in the dark matter, whether it's cold or not, which is kind of an outrageous concept. If you think about it, it isn't. But it sounds really weird. What is the entropy of cold dark matter? But it's there. And then in a Bose-Einstein distribution with zero chemical potential, there are 5.2 bits per photon. And with a neutrino Fermi-Dirac distribution with zero chemical potential, it's 6.1 bits per neutrino. Now, what does that really mean? It means something about how random things are for each of the particles that's present, telling you at some level how hot it is. The photon entropy per baryon goes like T gamma cubed divided by m baryon. The total matter and radiation entropy in the Hubble volume, essentially our observable universe, is 10 to the 88.6. And the ludicrous thing about this is that we actually know the 0.6 number. amazing thing. The dominant entropy baryon is in the microwave background in the cosmic neutrinos coming out of the Big Bang. But as I mentioned, most of the entropy in waste heat, most of the entropy after that in matter is in the waste heat from dust re-emission of starlight. So that this is the third basic ingredient, the cosmic infrared background, which is why it's so fundamental. It's the waste heat of the formation of galaxies. If you ask about the entropy in all of the clusters, it comes out to be about 10 to the 76, significantly below this number, of course. And then I talked about the story of how this is all compressed, all of this huge information storage is compressed into these cosmological parameters. That's something I'll introduce in a bit called information quality. But then there is this whole other thing, which I used to just put aside and say, we can't really access that stuff anyway, which is the gravitational entropy. In the universe at large, it's called the Gibbons-Hawking entropy. And it goes like the Planck mass squared divided by the Hawking temperature squared. The Hawking temperature is related to the Hubble parameter. This is the inverse of the Hawking temperature by this relationship. Radiation temperatures are kind of the square root of that. But the main point here is that this is a large number. It is related to what we call the conundrum of why the dark energy is the value that it is, which is about the inverse of this number times m Planck to the fourth. Anyway, that's neither here nor there. Now I have understood that this is actually playing a fundamental role in the whole inflationary process. The one that we do not get to play around with very much is the gravitational entropy of black holes. And that's because the lifetime of the black holes, if they're large or even stellar, is far, far too long relative to the age of the universe that you can't access the Hawking radiation that's coming from those black holes. It has to be much smaller ones, some that might blow up in the early universe. Anyway, so this one is still an outlier in terms of engagement. So what you get the impression of here is that there is a entropy which is decreasing as you go more and more towards more concentrated entities. And supernova core being an example of that. And so that's telling you that what's happening in the flow of information in terms of the formation of cosmic structure is that somehow it's getting rid of all of this entropy. Well, you know how that happens in stars. It's basically happening by radiation, photon radiation, or in the late stages by neutrino radiation, but it's also happening by convection, which is trying to make the entropy uniform by doing turbulent cascade, moving it out. And that's the phenomenon of the red giant, that once you've exhausted hydrogen in the core collapses and the excess entropy pumps out the halo. So it's a core halo phenomenon. That's why halo is misused, in my view, in cosmology. It should never have been introduced, but it was. So just to go back a little bit to this ancient history, when I was effectively leaving Caltech, I got into non-equilibrium thermodynamics. It was part of this talk with Beta. And Prigogine had gotten the Nobel Prize around that time for what was called non-equilibrium thermodynamics. But what was that? It was essentially, if you were a small difference away from equilibrium, then you had a description of the system which would be accurate, and that was called non-equilibrium thermodynamics. And then they threw up their hands to say, but I can't deal with a system that's very far from equilibrium. But I say that's not true. That's just quantum transport, with this insight. So one of the things that comes out of this is, first of all, anyway, there's a law, I won't get into the details, but there is this concept of an entropy current, which arises in the Purgagianisms, where you're taking these inverse temperatures and you're multiplying by the energy current, momentum current, it's something else, and then there are the minus chemical potential times the inverse temperature, which are these alphas, and George will recognize the alphas, as will Evan, who's on the who's listening to this, and that is a system which is describing far from equilibrium transport. But now the problem with that is that it doesn't make that much sense. You can put the fourth dimension, the time on this, so it becomes a forecurrent of entropy, which you're not used to thinking of. But what it does, it splits into all these components, and they can move at different speeds, and that is the speed of information flow. And for some reason, which we do not understand, there's a maximum speed to entropy flow, which is the speed of light, and asymptotically the speed of neutrinos. So now we understand that this is a general system where the entropy is this alpha C times NC, where now we reinterpret the momentum and the energy, and we divide by a scale for energy and a scale for momentum. So it all becomes counts. How many energy counts are there? How many momentum counts are there? How many counts of different species? How many counts of baryons? How many counts of leptons, et cetera, et cetera. So this is a very general framework. And this is count. And this is the dual of count, hence the paper with George and Evan and Joel Myers. This is like a current. You put mu on it, and it becomes a number current. And this, what do you think that is? It's also should have a mu on it, which is like a current, but it's the dual of the current, which is called a gauge field. I'm saying things that you know, but you probably don't know it in this terminology. And if you're looking for the tensor quantity or a relativistically invariant quantity, it would be a tensor and not a current, an entropy current. It's an entropy tensor, which has components which give all sorts of possibilities for interesting anisotropy. We'll try and go into this later about the relationship between action and entropy and how one can understand the whole inflationary phenomenon as a flow from action to entropy. Okay, so I say this because I've been doing this for a long time. And as George will attest to, I've been crazy for a long time with these out-of-the-box ideas. So the way I do my work is I write to myself. And at some level, I don't care very much if anybody likes it, because I like it. It is to myself. It is my self-development. Anyway, I came across, I have a huge number of books from those eras. The idea is that entropy is imaginary action. Obviously, that has stayed with me all this time. And the belief that inverse temperature is imaginary time is profound, and that action and entropy principles are the key to physics. And so instead of one thinking that I'm going off the deep end with these ideas now, I was always off the deep end, but I think that this is the right approach. Okay, I'll say a few more words about entropy, though. Entropy is a measure of quantity. And there is another concept which is sort of in the eye of the beholder, and it is kind of ill-formed, but I'll try and explain what is meant: information quality. And you're used to the word quality when you deal with oscillators, which have some damping. So we call it frequency, or real frequency, times the damping time is called the quality. And so if it's oscillating like this with an envelope like this, then the quality is high. But if it's going up or going down with very rapid damping, that's a low quality situation. And to a very real extent, that is information quality. And what we do when we gather all of this information that flows through us from the universe, is we filter it, compress it, reduce it, and marginalize it. That's how we find the fundamental information about the universe. And so one way that this is worded in the ideas of probability ideas is one version of this is that it's a minimal length message or code subject to an error tolerance. I won't try and explain that in detail, except that it has message, the medium is the message, and that the message is kind of a code describing how things go. But you can also think that an equation is a information quality compression of a lot of information. Recipes to make things, it's the same thing. And so the way I view this, and this is really useful cosmologically, is that what you're trying to do is you're trying to take the entropy that's coming in, this huge volume of information that is radiating us at all times from the universe, and we're radiating out as well. And what we're trying to do is expand it in what you might call prominences, that is to say, big ideas, major things. So that, so the example in cosmology, artificial intelligence is much like this, by the way, but in cosmology, we expand in what are called halos, which are concentrations of density that occur. And an expansion in halos is an expansion in prominences. So instead of dealing with the really short distance stuff and trying to do everything for a minute, you end up saying, yeah, but you know, there's this big coherent entity, which we're going to call a halo. And I need to characterize that. And at some level, that's more important than all the little fluctuations. It's like saying Mount Everest is more important than the tiny little ridges, et cetera, that make up Mount Everest. You look at Mount Everest and you see a gestalt, a whole. It's the same kind of situation. Anyway, I could go on to with this forever, but otherwise I will never get anywhere, which is typical of me. Okay, so this all leads to transport, and Evan, listen to this. It is all about what you guys like to call quantum kinetic theory, but it is really just quantum mechanics. And it's far from equilibrium transport. And the fundamental entity is the density matrix. But if you reduce the density matrix to single degrees of freedom, it becomes what's called the Wigner distribution function, which is usually how these things are done. And the entropy or the action, they're driven out of equilibrium by this variable alpha that I referred to, which is like a gauge field, but it's dual to the count. And in fact, its relationship, at least in some limit, is that it's the derivative of the entropy relative to the count, but that's what it is. And the total entropy is the sum over all of the components. And you could say the components make up a catalog. Catalog have a certain descriptive aspects to it. And the elements of the catalog can be quite microscopic, or they can be fundamentally microscopic. And the whole history of physics at some level has been trying to say, oh yeah, but there's some fundamental microscopic variables that make up everything. But then there was the revolution that I would say Anderson was one of the big players on, which is to emphasize that the development is all about emergence, and you can emerge large collectives that you wouldn't necessarily figure out are there by, you know, working with the fundamental quarks. And so it's a description which has got all possible aspects of collective phenomena in it. I could go on about this. Here I'm referring to the division by a scale in order to get energy counts that go into the general description. I don't really have time to talk about how I'm thinking about this now, because it isn't just that the Wigner distribution function has phase information, phase differences, and counts in it, but you can also think about it as if it's transforming from an initial state to a final state. It's another way of looking at the same phenomenon that you usually deal with in terms of splitting the variables like x final and x initial into a little dipole and a coarse graining of space. That's too many words right now to absorb, but there's a whole different way of looking at the evolution of distribution function. And that distribution function then has a lot of ingredients that are quite like the S matrix, but it's for general fact in the S matrix. Okay, and then there's transport. And transport is taking a Wigner distribution function in time and it transports it. And there's basically a general relationship, not much realized, but that's the way it is, that there is an entity which is the equilibrium that each component in our catalog is trying to get to. And then there is a rate at which it approaches that. So the way we usually do this, and the way Evan and George and others and me in the past have done this, is you calculate the gamma and the NCX by Fermi's golden rule. And so that's a standard way to do it. But you could also say, well, these are dynamical variables and they change, because what's actually happening is that the system is always trying to relax to a new equilibrium. It's an attractor, but it never quite gets there because this thing evolves. And so you could imagine a situation where you replace the full hierarchy of transport in terms of a dynamical equation in which gamma evolves and the equilibrium evolves, as well as the count that you're trying to take account of. Okay. BFGMW 24. What do you think that is, George? Bohr? Evan Groth was on the line. Joel Myers. We had a student working with us at the beginning of this. We did this transport and basically this whole framework by doing homogeneous transport of the cosmic neutrino background. Our next big thing, or there may be many big things, but one of them is to add the spatial fluctuations, which may have a certain roughness to the neutrinos with all sorts of really interesting physics that can arise from this. But I also plan to rewrite transport, which I've been doing my whole career, in this language for the photons, gravity waves, and all of that in these variables, because it turns out that it was much better than what I used to do in the old days. Usually the photons were dealt in a perturbative framework when we were dealing with the microwave background, but we have to be aware that they can be non-perturbative, and this is the better framework for dealing with the non-perturbative aspects. So now this will look silly. This is, but I've been showing this for a billion years. Well, it's like exaggeration. You can see the it from bits in it is already there. CETA, Cosmic Information Theory and Analysis, with a Q in front being quantum. Question mark is the beginning, emergence, which we still don't know about. So I used to describe this as it was a dragon that was breathing this fire out from the Planck era. And that's basically as good a description as any, even to this day. The question of emergence is huge. And it's something that I have a lot of fun thinking about. And then we pass through all of the epochs of the quark-gluon suit. There's a transition, which is like a phase transition, when you pass from an inflationary realm into heat. And I refer to this as the shock in time, where there's a sudden change, and it looks like a lot of entropy is developed. Because it is. That's where the entropy is supposed to come from. It could be that there are particle decays and second order phase transitions along the way, but so far we have no evidence for a first order phase transition in the expanding universe, that is to say, the quark-gluon plasma, etc. Or it could be small. When the neutrinos decouple, which is right around the time that the protons is stuff that work with George and company, there's a little bit of entropy generation there, but it's quite small. If you have roughness, there will be more. When the photons are released, well, first of all, they cease to be a Planck spectrum, or could be, at some period about 10 to the redshift 10 to the 5 or 10 to the 6 or so. And then Thomson scattering is the final breakout at redshift a little over 1,000. And then the photons come to us, the matter starts collapsing, and then it's doing all of the usual things in formation of light. There we are, our good friend Schrodinger, and cosmic web. And then Pythagoras got created, so we could look at this and try and understand it in its sense, kind of using in its way. So I'm going to focus a little bit on this epoch, because you aren't usually used to thinking about entropy with large-scale structure and what that means for those structures. But entropy plays a role in every one of these cases. Yeah, so we used to say that, well, we didn't actually, people didn't understand really what entropy generation was all about, because it looked like you could do entropy just by a density fluctuations getting bigger and bigger, but that's a different kind of entropy. And so we used to call this shell crossing, so that you have a shell of matter which crosses, and that effectively means that you can't have a coherent description along the lines of having a gradient describing a flow. So it's like having a transition from a laminar flow to one with a heat content in it, which is basically that K space splits into a number of components of momentum. And so I'm now calling these gravitational shocks, because that's really what they are. And gravitational shocking is what gives you the entropy and the dark matter, and associated with structure formation. So that's one of the main origins of entropy derived from gravitational collapse. It's what gives the clusters that high entropy per baryon that I referred to before. And I could go into the details of this. This picture here, which I'll show in more detail later, I don't know if you can see it. It's got all of these kind of cosmic web filamentary things associated with it. That's actually a picture of entropy. It's, you know, projected. It's 2D, but projected from 3D. But the important point is that it's tracing the cosmic web. So the entropy and the cosmic web are intimately associated with each other. I'll riff on that for a minute, but not long. But a way to understand this, do I really want to show this? It's kind of fun though. I wanted to have a description of how best to explain this kind of phenomena. And we were having a birthday party for my good friend Simon White and Carlos Frank in Argentina. And we went to a tango place in Buenos Aires. And this is a picture I actually took, all power to me, at a tango club. And you know, the thing about a tango is that the legs of the two dancers are traveling at near the speed of light, and they're entangling with each other, but they never cross, which is exactly what happens in a cold dark matter sort of scenario. You have a phase space, and you have these phase space streams, and they never cross each other in phase space. If you project them, they cross each other. That's the shocking. But they maintain, so that if you look at things at an arbitrarily fine grained point of view in a cold dark matter model, you don't have any entropy, in spite of the fact that it looks very complicated. But as soon as you do a little bit of coarse graining and say, well, I'm looking at it in a fuzzy way, you see that entropy arises. And so this is kind of a paradigm. And the reason I liked it, it's because it's all about entanglement, which of course became entanglement. in this story to my good friend's birthday party. And then when I was in India, I decided there was another way to describe the entangling of the different phase-space streams by Shiva. And the dragon is what I used in China. So entanglement is fundamental. So I'm not going to spend time on this. This is a picture, gas dynamical, of pressure, which is cosmic web, but it is, you don't see all of the filamentary stuff because the pressure is highest in the clusters. And you know, in groups and things, it's reasonably high, but it's not so high out here, and that's because the temperature is low. So that's the cosmic web as seen under pressure, and we spend a lot of time looking at that. And there's in the entropy, it turns out that in the gas, there's a profile that is almost universal that appears, and more to the point, with dark matter, it really is universal. It's a very simple form, which I won't get into, but for those of you who know the names, the NFW density profile, which is a usual way to simply describe the density distribution of dark matter, more profound, more robust is this relationship of entropy per dark matter, which has a very, very specific kind of growth pattern. The magnitude is about 7 bits per dark matter particle. The universality of that, which is a description of high nonlinearity in the system, is really quite remarkable. I won't get into this. This is some of the applications that we do with the subject, where we make maps, and the maps are of observable phenomena, and entropy is not an observed phenomena, it is a derived phenomenon in the universe, so you have to bring things together to do it. But this is sort of making catalogs of things. Do we want to do this? I probably want to skip over this, but I did want to emphasize this gravithermal instability as a way of looking at things, which is this core halo gravity flow compared to entropic flow, which is outwards, gravity flow inwards, and that there are two kinds of instabilities to consider. The usual instability that one thinks about is that everything is trying to go towards a black hole. That's kind of the so-called equilibrium that things are driving towards with gravity. What it's doing is it's trying to concentrate the mass in the black hole and put everything else into a void. And that is exactly this core halo phenomenon where the entropy is being radiated outwards. But nobody really looks at it like entropy is radiating outward. And so there's a whole study to do on this, which I want to do, associated with this. And so there was this comment in the famous Misner, Thorne, and Wheeler book, which is that the universe is that which is always trying to straighten itself out. And I always thought that was quite mysterious because we all think of gravitational collapse when you're dealing with gravity. But it's the entropic flows that are the thing that's actually dominant, that's creating all of this kind of void-like regions with these concentrated nodes. And of course, the nodes have dimensionality so that the zero-dimensional node are the clusters, the one-dimensional nodes are the filaments, the two-dimensional nodes are the membranes, and it all goes in to make the cosmic web. So then that's a K-space instability where the wave number is going up and it's getting hotter. And there is a space instability, which you can think of as white hole production. There was a time when I was first starting out where white holes were considered to be verboten to think about because somebody demonstrated, unfortunately using classical gravity, that they were essentially like variations in the time of the Big Bang and that they would damp away. And that's not what happens. the expansion of the universe is the instability in X. And to a very real extent, that's like a white hole. And so, there's this picture now, nobody knows if it's true, where you have a black hole collapse, and then you have a wormhole, and out the other side becomes a universe, which is an X instability. Now that's really speculative, so I won't go further with that. So I'm going to give you what I think we need to do with the sets. So the sats were all designed at some level to see if from the ground we could get R, the tensor to scalar ratio. And that's assuming that both are effectively Gaussian distributed. That's what all of the designs have been in terms of observing strategy. So, and that's what bicep Keck does, right? Bicep Keck has a very small region of the sky because the concept is every region of the sky is going to look like every other region of the sky. And it's like a Gaussian random field. So this is a Gaussian random field with a scalar with kind of a standard inflation. And this is the associated gravity wave picture. And they both look rather similar only in the sense that they're realizations of a Gaussian random field. And the relationship between this one and this one, they aren't correlated with each other, but the square root of R is essentially like, which is the amplitude, the relative amplitude. It goes like the square root of this acceleration parameter. And so if you have a very small acceleration parameter, you don't get much gravity waves. And the issue is how small is that through the epoch of us observing. But these ideas of entropic generation and what I talked about was fission, fusion, and all of that. The picture of that, how that can operate in the universe, is that it can create what we call primordial intermittent non-Gaussianities that look like this. This and this were all part of one calculation that had a standard inflation, and it had a delta V that had an instability in it, so that if you're flowing down as the inflaton, instead of having the other directions all curled up and keeping you confined, you have an instability. And the instability causes all of the trajectories to expand. Now, if the trajectories expanded and then they all came back together and it was purely elastic, you wouldn't get the entropy production and you wouldn't get the observable signal. But they don't. And so this is a full up field theory calculation. This is the scalar part, and this is the associated gravity wave part. And you see what the point is. The point is that you get this, but it could be really small, but you can get this. And this has concentrated bits of scalar and concentrated bits, and this is the interesting point, of transverse traceless tensor component. And so how this happens is around these non-Gaussian entities, in the scalar part, you build a transverse traceless stress energy tensor. And that acts as the source of gravity waves. It's just a D'Alembert of the gravity waves is basically this quantity. So what happens is that you have this thing which is not into the center of the non-Gaussianity, but it's actually around the edge of it. And then there is an issue of how much you propagate when you first generate it. And at least in all these calculations, it was only a little bit of propagation. And then the issue is when it comes back into the horizon, is there a huge propagation that causes everything to overlap? Or do you still have this complete memory of the spottiness of gravity wave signature? Well, just think about what this would mean for the SATs and for Lightbird and all of these things, is that you would have to probe a large amount of the sky so that you wouldn't miss these things. And so it could be that we have bicep Keck on a little region and they miss the big signal. And nobody's really looking for this. And my contention is if we don't have something like this, then we are just going after the same old, same old. And what would be extremely exciting, but why would it be really exciting? It's because if we could find this and this, these would be correlated, and you'd be able to tell that they were correlated. So you'd be able to say a lot about how all of this stuff originated. And then the relative magnitude of this relative to that in the calculations is about 1 to 100. And so that's can be a lot bigger than this number. And so whether this is true or not, I don't know. But it is this whole new thing to go for. And it explicitly is, in my view, fundamental for the SATs of SO. And so it's something that we want to work on. But I think it's a good thing for you all to become engaged with, because it's a way of probing the data that's got a richness attached to it. And of course, you can see what the problem is. I don't just get this, I also get the dust B-mode. And so then you ask yourself, well, I have to separate the components. And so that's a whole new statistical game with a lot of new statistics required to go after it, and not the standard one in the way we've been doing things. So I, as you can see, I'm somewhat excited about this. And the entropic flow takes me to these ideas, because it turns out that the trajectories that give rise to these huge non-Gaussianities, it's a non-Gaussian tail, it's not just that they're intermittent, that they're spatially localized, but the ones that do the big non-Gaussianity are outlier. And so we're calling them primordial outlier non-Gaussianities. So it's the ping pong theory.
So how do we like distinguish non-Gaussianity created by the Planck, Coherent non-Gaussianity, and other second, other late time non-Gaussianity?
Well, I mean, that is the issue. But the way you do it, the way I think you do it, is you try and build templates. And there will be a template for this kind of signal and a template for the other. And if the templates look alike, you won't be able to tell.
Yeah.
But if there's enough separation of templates, then you can separate the components. So it's exactly like the component separation problem. But you have to build the templates in order to put them into the mix of component separation. And so that's the challenge, but I think it's a really worthwhile one, because, you know, we may get this, but we may not. But you've got to look for this.
Yeah.
And as you know, there are anomalies on large scales. We don't know what they are. And the standard thing to say is, well, you know, they could possibly be associated with Gaussianity. But the way this works is that, for example, the cold spot, you know, the cold spot, right? The cold spot would be because of, you know, something that was a little bit coldish from here, would have one of these things that would just happen to be correlated with it. It would build it up in magnitude. And so you would say, I can explain why the cold spot is 4.5 sigma, in spite of the fact that a Gaussian random field doesn't really get much above 3 sigma. And so that's a big deal. Anyway, I'm just saying that there is a way of understanding it. The trouble with the low L, which is our territory, is that we have sample variance, which is the real problem. So what you need is a lot of different things that you can especially correlate with in order to try and get to the key result. Anyway, I wanted to spend some time on this because I wanted to make sure that the people that were doing the hard work in Simon's Observatory could see that there's more than just the old story of going after everywhere gravity waves in the classic way, where people say, you know, it could be anywhere, and in particular, it could be really low. Okay, and that's, you think that's the end, don't you? And it will be the end, but I have to show you different versions of the end. I won't show you that. That was going into the multiverse. And so those two slides were the imaginary end of Einstein. And then the end of Bond's time for real. But what I'll leave is the last thing up here is all these relics that we have gotten in our cosmological journey, largely with the microwave background, but from the galaxies too, very much. And all these relics have this Superman sign or entropy sign beside them, because they're all associated with aspects of the entropy of the universe. First is the big thing, which is the structure from the early universe. The entropy that comes at the end of inflation, which is getting a 88.6 number. The baryon asymmetry, which is still a mystery after all this time. Dark matter, with its value so well determined from Planck. And you're going to hear some more of this from ACT tomorrow. And nucleosynthesis products, and then the neutrino background is all entropic, as my good friend here will bend your ear about. CMB and its fluctuations in polarization, that was really got a huge entropy thing. We're about to celebrate CMB at 60 in Italy this year. And then there's the whole galaxy thing, dark energy, don't get me started. Relation of this to the gravithermal catastrophe, etc. So with that, you will be happy to know, for real and Bond's time.